This video is sponsored by Creality. I decided it was time to get a CNC laser to make parts, labels and containers for the machined microwave devices that my business sells. The new 40-watt class blue diode lasers were the final push I needed. Then, out of the blue, Creality asked if I'd like to try their rather fabulous Falcon 2. Talk about serendipity. Right, let's be very clear here. I want a laser that as a machine tool, doing things that it does better than the traditional tools I use. I don't want to run a laser business. There's plenty of other folks out there making amazing stuff. I want to mark up control panels and cases for electronic and radio systems. I want to apply serial numbers and logos to tiny metal and plastic parts, build support structures to assist with machining and test fixtures, cut holes in engineering plastics that I can't do easily on a machine tool, and make protective wooden boxes for the high value items I sell. The Falcon 2 is small enough to fit on a desk or workbench and light enough to carry in one hand, if you're strong. It can work standalone, but it integrates really well with Lightburn. As well as the usual cutting and engraving, these blue lasers can develop reactive films on stainless steels to make a range of colours, including the blue that I use in my logo. This thing combines 8 5.5 watt laser diodes into a single beam. I've managed to slice through some pretty thick boards with it, although using it on 2x4 is a bit silly when I've got a big radial arm saw. For fine work, you can select a smaller beam that's great for fine engraving and where a cut needs to have minimal width. I'll measure just how fine a cut's possible later in this video. For me though, making joints is where this laser really shines.
I see what you did there.
Setting up the Falcon 2 is really simple. You just take it out of the box, fit the feet in one of the 3 sets of holes so it'll fit on different sized tables, slide on the head and connect the air assist tube to the pump that's supplied with the Falcon 2. There's plenty of videos about our process, so I'm not going to repeat it here. So, yeah. I'm not going to show you how to make decorations or dog tags or wall art or engravings of your cat, even if it is a lion or a tiger or bear.
Oh my.
Obviously, I might allow the occasional Chihuahua coaster, but I promise faithfully that I'm not going to encroach on anyone's business by putting hilarious messages on stainless beakers or engraving imperial eagles on glass pool trophies. I'm interested in how this gorgeous tool can help me make better products. I'm going to push things a bit with some materials way against best practice, but I like to know where the limits are. The most spiffy thing I want to try first is colour engraving on stainless steel. I'll try titanium alloys in a future video. This is my first attempt with a range of speeds and power levels generating black, 2 dark greys and 3 different blues. There's a lot wrong with it because I didn't use the right tools to make the source image and I've got no idea what I'm doing. Not that that's ever held me back. It's almost my slogan. Under a microscope, there's some definite scan lines in the blues and the slant lines are terrible because they're a raster image instead of a vector. But from a distance, they look very nice. I need to try different step over distances and some different dithering methods, but for a first attempt, I'm not going to beat myself up too much. I mean, Amy wouldn't be impressed.
That's mildly acceptable if you screw your eyes up and look at it from far away. Ideally, from very far away.
So, what did I need to do to get the Creality machine to do its magic? You can simply unplug the microSD card from the Falcon 2 and copy a generated G-code file from a computer and then plug it back into the Creality. When you press the button, it finds the most recent file in the root folder of the card and prints that. I'm a nerd and I wanted to do things a little more technically. So I decided to connect the Falcon 2 to the computer at the opposite end of the study. That's a problem because of the 3 metre limit of USB cables, but I found a 5 metre USB-A to USB-C lead with inbuilt range boosters. Links in the description. You can probably use 2 of these with a powered hub in the middle, but that needs additional nerding. Wi-Fi connectivity would be neat, but might encourage folks to leave the laser unattended with the associated fire risks. The Falcon 2's got excellent protective systems to detect problems with the air assist, fire detection and lens fouling, but leaving a CNC laser running unattended without a room fire suppression system is a little outside of my risk appetite. I wanted to sight the laser near an opening window and well away from where I sit in the study, so I could have the Falcon 2 running with my back to it at least 4 metres away for eye protection and lung protection when I'm cutting smoky and smelly stuff. Now, it's important to say that the basic machine doesn't include some of the quite useful accessories I've got. The separately purchased honeycomb support plates, really useful for felt, leather and other floppy materials. Also, when I'm using some sort of cutting template. For stiff material though, I prefer building support pillars with disc magnets for the material to rest on, and then another 2mm thick disc magnet on top to grip the workpiece. Sometimes when you're cutting wood sheets, even with full air assist, there's a little soot deposition on the underside of the material where the laser hits the honeycomb. Using spacers, either on a mild steel plate or the honeycomb, fixes that and gives a nice clean underside to cuts, though it needs a bit more faffing about to set up the parts. Another useful accessory that's really vital for indoor use with wood, plexiglass or leather is the enclosure. It's a very simple aluminium lined fabric on a pushed together rod frame with 2 fan ports for fume extraction and 2 rubber star gaskets to get the leads from the outside to the inside. The enclosure isn't included with the machine, but it's practical and affordable, so I'd really recommend getting one. One of the vital steps about using a laser for cutting or engraving is test grids. The speed and power of the beam need to be balanced so you can get a nice clean cut in a reasonable time. So I tried some cuts and fills at a range of speeds and powers. I'll be keeping them in a file for reference for each type of material. This one shows me how 3mm plywood behaves. Based on the test grid, I chose 800mm per minute at 90% power as a reasonable value for cutting. I ran some 20mm square cuts and a 24mm round cut using zero kerf in the light burn settings to see how accurate the laser was in the X and Y directions when I wanted to make a cut with a very precise inside or outside dimension. I used a stack of gauge blocks to measure the X and Y dimensions of the square holes and then used a 3-point bore micrometer to measure the 24mm round hole. I used the measured dimension so I could set the right kerf offset. Now that cutting was sorted, I decided to make a finger-jointed plywood box for some of the small antenna system products I make. I know there are fancy websites and Python scripts so you can just specify the size of box and the code does the rest, but I'm a nerd, so I made a parametric model in Fusion 360 that makes boxes in the style I prefer just by specifying the thickness of material, box dimensions and how many fingers per vertex in height, width and length. It works fine, although I should really include the kerf compensation so Lightburn doesn't have to make any inside versus outside decisions, and I won't have to specify extra nodes with different kerf offsets for vertical and horizontal. After a tweak to the kerf offset, it goes together nicely. The logo's nice and crisp and there's no smoke stains because I used painter's tape. I had to do a few tweaks to get the kerf offset just right, but now I can reproduce it no problem at all. I tried thicker plywood, but the glue in it wasn't really suitable and it set off the fire alarm in the Falcon 2. Loads of smoke and the air assist rather fanned the flames, but kept the smoke and heat well away from the laser head. After putting out the fire, I cleaned the lens and tried other plywood boards up to 1/2 inch thick, and they cut nicely with no fuss. I tried some spruce boards 17mm thick. They needed 2 passes, but cut very cleanly, and made some excellent well-fitting finger joints. I cut the slots 1mm too deep so I can sand off the excess burnt wood and leave nice clean faces, but actually I rather like that brown contrasty finish. When I'm making pieces of radio equipment and test gear, I like to have a nice neat front panel. Getting that really crisp result in the past was awful. Anyone remember Letraset and water slide transfers? Best forgotten. Now I can machine a piece of dyed anodised aluminium to size, cut out a support template exactly that size in thin plywood, then hit the anodised material with a laser. The dye in the anodised layer either bleaches, dissociates or sublimates, leaving a nice white line or block. If you use too much power or too slow a speed, it goes silver, perhaps exposing the raw aluminium. I ran test grids to find the best white and then used those settings to make a quick sample in Lightburn. I got a bit overconfident at this point and decided to try some 150 micrometre stainless foil. That's 0.15mm or 6 thou or mil, bit thicker than a sheet of printer paper. I tried a simple straight cut, but foolishly I placed the material on the honeycomb bed. I should have clamped it in a fixture. The cut welded itself to the honeycomb in a couple of places, making the edge a bit raggier than it should have been. An 18mm hole cut through okay as well, but I think I need to try some better fixturing and play more with air assist level and speed and power. I tried a test grid for cuts and it was pretty disastrous because the material warped and twisted and bent and soon hit the laser head and got pushed out of the way. I'll try more experiments in a future video. Only slightly defeated, I tried cutting some copper foil, which should be impossible, but I used 10 µm foil and put low-tack painter's tape on the upper face, laying it all on a sheet of plywood. The laser cut it very easily, but there was some rippling around the edges of the holes. I might try it fixed between 2 sheets of clear glass with paper on top of the foil. I think the best way to cut thicker copper foil might be to paint the copper with an X-resist varnish, laser it both sides using alignment pins, and with the rear image being inverted, then perhaps electro etch or use a chemical etch to remove the bare copper from both sides until it's all gone, and then finally dissolve the resist in acetone or DCM or limonene or something. The next material's brass. Just for giggles I tried a full power etch, but it just left a rather blurry and very shallow mark as expected. Then I tried some brilliant spray on the brass. It goes on as a very fragile white powder layer once it's dried, but once you hit it with the laser it turns a very dark shade of brown, close to black, and it adheres ever so strongly to the brass surface. It's very robust and the contrast's excellent. It's cheaper than Cermark, but not by much. Links in the description. I love this little unit. It's reliable and convenient and fast and tidy. Let's see how it deals with plastics. It's supposed to be able to cut breathtaking thicknesses of acrylic, but the colour really matters. I tried some cuts in black acrylic from a Chinese source and some thicker material that's branded as Perspex. Again, it's black. They both cut well with a slight amount of banding on the edges. I tried cutting out my logo and it handled that well. I adjusted the kerf width to 0.1mm on the outside to try and get the letters precise. Certainly seems to work well on the black material. I went for broke and tried some dark blue acrylic, which definitely should not work. And that confirmed it. It really isn't working properly. I tried some awful pink acrylic with a test grid. That was a major fail. Best consigned to the trash can of history. Another thing I can't make easily but really need is felt washers to fit under bolt heads and steel washers holding plastic sheet materials and other brittle things. In the kit there's some lovely bright red felt-like material, so I made some washers from it. The material seems to be some sort of man-made fibre and the edges have sealed nicely. I do have some real wool industrial felt used for way wipers that I'd like to try. Perhaps that's something for a future video. For masking large areas, I find it best to use a foot-wide roll of masking material and use a rubber roller or squeegee and burnisher to get a good contact with the material. I use Gorilla brand duct tape to help peel off the mask after a cut. That stuff's really sticky and helps lift the little fiddly bits of tape. I also use some electronic tweezers and a surgical scalpel for really fine work under a magnifier or a binocular microscope. The plastic razor blades that come with a holder also work well, links in the description of course. If you'd like to support my channel, you can join my lovely patrons over on Patreon or buy me a coffee on ko-fi.com. Links up at the top and of course in the video description that nobody ever reads. I'm not going to go into using paint fill of engravings in this video, but soon I'm going to need some signage for my business and I'll be using resin pour, masked spray paint and powder coating paint on signs and perhaps on wooden cases for instruments which aren't semi-disposable like the simple plywood finger joint boxes. Something I'd like to try is making a vacuum bed to hold down thin plywood or acrylic that's slightly warped, but also to provide additional air assist by sucking smoke downwards through the honeycomb and out to a vent using a more powerful fan. Might work with foils as well. It makes sense to check the alignment of the machine when you get it, but perhaps not to the extent I did. Mine was pretty much perfect out the box, but making adjustments is easy enough using an engineer's square. There's good instructions on Creality's channel about setting belt tension and ensuring the gantry is perfectly aligned. I'm going to check belt tensions and the shaft rollers once a month to make sure everything's still hunky-dory. I set up the Falcon 2 on my granite surface table, which is flat and level to within around 10 micrometres, and used a surface gauge and dial test indicator to check the distance from the reference plate to the corner of the laser head across the full range of motion. With all 4 feet finger tight, there was about 40 micrometres of error across the full x-axis range and 200 micrometres across the y-axis. By adjusting the feet and using a machinist level and a 2 micrometre DTI, I nulled out the errors to better than 20 micrometres. Very impressive indeed. In a future video, I'll set up a dial test indicator to find how close to true straight lines and circles the Falcon 2 can manage. That should be interesting. After checking for squareness, I found the sides are symmetrically bowed inwards by about 500 micrometres, but it didn't affect the precision of the traverse on either axis. The bowing was symmetrical and effectively cancelled out any errors. I decided to adjust the eccentric nuts on the laser head and on the y-axis slides, although actually they were pretty close to optimal straight out the box. Belt tension was also perfect, so I didn't mess with it. To finish the small finger jointed box, I made a liner from dark grey EVA foam, cutting a test grid using the precise setting of the laser. The cut lines were very clean and straight with no ridges or melting. I glued the slices together to make a 3D cushion for an SMA to WR90 waveguide transition. My first attempt, and it just worked. I'm confident in the performance and reliability of the Falcon 2. It feels like a finished and complete product, not a flaky development project that's going to need care and feeding and in getting involved in geeky stuff. I can just use the thing like I use a hammer or a chisel or a milling machine. Very cool. And finished off with engraved text and a QR code engraved on the lid as the cherry on the cake. I wanted to check if there were any artifacts or weirdnesses with tiny increments of parallel and radial lines, so I ran some torture tests to see if anything showed up. There's a faint suspicion of pairing of radial lines where a stroke goes from one side of the circle to the other, moves around the circumference by 1 degree, and then goes back to the opposite side of the circle. It's hard to be sure, but there's some very, very minor effect going on. It could be an optical illusion caused by the very real effect that when the laser head's accelerating, it starts at low power until it's up at full speed, then it slows down again and cuts the power towards the destination. But it maybe does a deliberate overshoot, so there's a very sharp cut-off and you get a dark ending to the line. Alternate lines appear shorter and lighter as a result. It's being super picky and you get the same effect when doing an area fill. There though, you do have the option of unidirectional fills to help avoid the comb-like appearance of rectangular fills. I might try coding up some programs to generate G-code that avoids the issue using deliberate overscans, but I rate this as a highly successful response, and for a machine that's designed for speed, it's a very good compromise. Excellent. One of the key features of the Falcon 2 40 watts, the maximum top speed of 25,000 millimetres a minute. I'm an engineer and I work on the trust but verify model, so I set up some test patterns moving at speeds of up to 25,000 millimetres a minute according to Lightburn, with only x-axis movement, and then separate tests with circles, diagonal lines and a y-axis traverse. I used a stopwatch on a smartphone to give me an independent source of elapsed time. On a long x-axis traverse, the speed really does exceed 25,000 millimetres a minute once the laser head's been accelerated, which takes nearly a third of the traverse, but then obviously it's got to slow down again. So the mean overall speed from a standing start to a full stop is around about 13,000 millimetres a minute. There's a lot more mass in the Y direction, obviously, because you've got to move the whole carriage. The average speed for the same 380mm stroke is 7,400 millimetres a minute. Circles with a radius of 380mm average about 11,500 millimetres a minute, as do diagonal lines of length root 2 times 380, just as you'd expect. I did detailed tests on the cut width at various heights above the workpiece to find the divergence of the laser beam and check the kerf width at normal and precise resolution. I used a stepped fixture with small test coupons cut from 3mm plywood, and then did a detailed analysis of the real size of rectangles in both planes in standard and precise settings for a range of kerf offsets to find the optimum for my material, which is this 3mm ply. Life is too short to go into that now, but Spoiler alert, a kerf offset of 0.1mm in standard and 0.075 in precise gave the best results in this specific 3mm ply at the specific settings I used. I'll probably go into these findings in a lot more detail in the next video in the series. As for safety, yes, there are serious risks of eye injury and permanent blindness on any visible light laser if you get even a momentary flash from a reflection. Unlike the long-wave infrared from a CO2 laser, your eye is designed to be super efficient with visible light, and your retinas get no natural protection. The filtered cover on the bottom of the laser head certainly helps, and in conjunction with the safety goggles and simple practical steps like staying the heck away from the machine while it's running, it's going to be safe enough so long as you keep humans and animals out of the area completely and lock the machine if you have kids or idiots in the house. Back in the 70s, I somehow had a laser burn on one of my retinas. It wasn't spotted until I went for a computer eye test in the 1980s. "Ooh," the ophthalmologist said. "Where do you get the cool laser burn?" "What laser burn?" I said. I used some strong UV sources in experiments, and I bought some horribly expensive professional goggles with an OD7 rating for UV through right to the end of blue, so I used those. I haven't measured the performance of the goggles in the kit, but please use them. The cover's a low-cost addition that really helps control smoke and fumes. The supplied fan's pretty quiet, but it's also not very powerful. I'd consider using two much chunkier fans and using the minimum length of hose stretched to ensure good airflow. Don't just poke the hose out of a window. The fumes will probably just come straight back into the room. I cut some foam blocks to help seal the gap in my window and fit around the 3D printed adapter. The result's almost no stinkiness and very little smoke leakage back into the room. Overall, I just love this little machine. It's so much more adaptable and portable and convenient than a big CO2 laser. I like the repeatability, I like the precision, and I like the switchable laser head setting for fine detail work or full power with a wider kerf. I like the way it works straight out the box with light burn, as long as you read the instructions and copy the settings from the SD card to the computer like the folks on the forum seem to fail to do. There are some affiliate links in the description if you'd like to buy a machine or accessories. I'll get a small commission to invest in more content. What's not to like? Huge thanks to Creality for sponsoring this video. It's been a real eye-opener for me to see the real business benefits that this generation of CNC lasers can deliver at a relatively sensible price point. I'm enormously grateful to my Patreon supporters and subscribers for supporting the channel. There's a lot more projects in the pipeline. The next video in the series will be up there.